We're going to talk about science, an amazing discovery, and we're going to talk about the doing of science, how it gets funded, how it gets worked out, and we're at a Humanities Festival. Now, I know, because I've talked to these people, that we have none of the three of us have any problems with this. But I thought it was worth saying just up front something a little bit about why we thought this would be an excellent event for us at the Chicago Humanities Festival, Fall Festival. At CHF, we often find ourselves defending or promoting the concept of imagination. Imagination allows us to think of things that are unreal, are utopian, or sometimes just impossible. Science puts a different kind of tax on the imagination. It asks us to conceive of things that are real, that have been discovered, but that are of such magnitudes or complexity as to defy conception. And certainly one of the results of the discovery of gravitational waves just last year is to ask us that task of imagination. So we'll have a little chance to do that kind of work today. Before we go any further, I'm going to ask Nergis to give us a run through some of the science behind the discovery, and we'll take about 10, 12 minutes to do that, and then we'll sit down again and we'll go from there. So Nergis?
Thank you, Jonathan, and thank you everyone for being here. So what I want to do for the next few minutes is simply to unpack for you some of the science that went behind this discovery that was announced, and some of you might have noticed it was announced in February earlier this year. Now, the discovery really is about gravitational waves and black holes, but to understand gravitational waves, we must first think about gravity. Now, almost all of us have experience with gravity. Without exception, we jump up and we land on our feet. Well, most of us do. So we know gravity is out there. And this picture of gravity was given to us by Isaac Newton actually in the 17th century. Now, gravity as a theory and the way it worked wasn't complete. There were things about the universe already within our own solar system that scientists didn't understand. And there was one really interesting question that Newton himself asked that was never solved in his lifetime. He asked how his theory told the moon that it should go around the Earth. It should orbit the Earth. And the question he asked was, well, how does the moon know about the Earth? What is the thing that sends this information out to the moon? And that question was not answered till our next hero of gravity, who was Einstein. And this was in the early 20th century when Einstein formulated his theory of general relativity, which is really a theory of gravity. And what Einstein said was, we should no longer think of gravity as a force. It's not a force of attraction. Gravity is geometry. And we've all famously seen a picture like this one where you take some object in the sky, in this case a sun, say, and because of the geometry of space-time, Einstein said space-time is just a grid. And when you put something heavy on this grid, it will deform the grid, just as if you put a bowling ball in the center of a trampoline. And that was the picture of gravity that Einstein gave us. And then it's very easy to understand Newton's conundrum, because if we now put a little Earth at the edge of this curved space-time, that little Earth will fall along the curvature and collide into the sun. Or if the Earth is orbiting, it will stay in that orbit. So that was the picture of gravity. Now, Einstein had one other thing that you really had to add to the theory. He asked the question, what if the star wasn't just sitting around? What if it was accelerating, moving? And then he found something remarkable. He found that the entire space-time around this object would ripple, just like if you dropped a rock on the surface of a smooth pond and the ripples on the surface of the pond would spread out from the rock. So also if you took two objects, in this particular case I've drawn, there could be black holes or neutron stars, which are a very particular kind of star, you would see waves along that sort of ripple all over space-time. So never again will you think of space as just empty and doing nothing. Space curves, space warps, space ripples. Okay? And it does that only in those parts of space where very, very massive objects occupy it. So in the case of our own sun, we get a little bit of curvature and we get the orbits of the planets. When you get to very, very massive stars like black holes and neutron stars, then you can get very serious curvature. And many of us have seen famously these diagrams of a black hole with a funnel under it. And that's the curvature of space-time when it's so curved. So this, armed with this, now it turns out Einstein, this came out of the mathematics of his theory. He himself was very, very unhappy about it and quite ambivalent about the very existence of gravitational waves. But the remarkable thing is that despite how ambivalent he was, his theory actually was very correct. And so this is a movie of two black holes. So black holes are stars that are so massive that even light cannot escape. So they have a lot of gravity. And this is a movie that solves Einstein's equations to tell us what would space-time do when two black holes orbit each other. And because they're radiating away these gravitational waves, the energy carried away by the waves comes out of the orbit, and the black holes get closer and closer to each other, and eventually they collide. And down at the bottom is the signal that you accumulate as this process happens. The curvature of space-time is shown on the surface there. And since this is the theme of our event today is time, the arrows show how time flows in this space. Now, the movie has been slowed down deliberately to show what happens when the black holes just touch. And you can see that space-time distorts in a spectacular way. This is a region of space you do not want to be in, okay? Now, eventually, the black holes collide, and they form one single black hole that wobbles a little bit and then is quiescent. And then these waves propagate out into the universe. And that is the process that Einstein's equations taught us that gravity could do. Completely different from what Newton could do. In Newton's gravity, there were no waves. And in fact, there was no ability to make black holes the way we do in Einstein's theory. Well, this was... Einstein remained ambivalent about this almost his whole career. And part of the reason was that he actually, in his lifetime, neutron stars, which are very dense stars, they're actually stars that have the mass of our sun, but are only 10 kilometers in radius. So they're about the size of Evanston, but has the mass of our sun. The reason his ambivalence was valid because these had not been discovered. But in the 60s and 70s, people had started to ask the question, since the discovery of black holes and neutron stars had come, what would the signals look like? And so here is what Einstein's equations would tell us. The signals would look like this set of bumps and wiggles as a function of time. That's the amplitude of the wave, or strain. The person who first started to think about these calculations was Professor Kip Thorne, who was a professor at Caltech at the time, and an important player in the history of LIGO. And he found, and along with colleagues, something really startling. He found that the size of the wave was this horribly small number, which we write as 10 to the minus 21, 10 to the power of minus 21. Now, let me just put that in perspective. That's a decimal point with 20 zeros after it, and then a 1. Okay, so it's a very small number, and it's because gravity is inherently very weak. And that's what we were finding about the effect of these waves from neutron stars or black holes here on the Earth. Now, in the meantime, Professor Ray Weiss, who was a professor of physics at MIT, was thinking about how one might detect such waves. And he came up with the idea of using an interferometer. So let me just say, to ask how one might detect waves, you have to ask, what do they do here on the Earth? Right? I mean, if you wanted to detect the falling rock on the surface of the pond, you might put a little boat at the edge, and when the wave comes by, the boat bobs, and you would know a rock had been dropped. And his idea was similar. So what do gravitational waves do to us? They distort the space-time as they travel through it. So as a wave from the distant universe travels through me, it is stretching me in one direction and shrinking me in the other, and then vice versa a half cycle later. So as it passes through me, I would sort of go stretched and shrunk. Now, by very, very little, but that's what the effect is. And he noticed that an interferometer is a good device to make that measurement. Because if you see the interferometer drawn over here, it's a device where you start with a laser beam, you split it into two halves, reflect it off of two mirrors, and you recombine that beam. And by measuring the light travel time along one path compared to the other, you can tell which path was longer or shorter. And as a gravitational wave comes through that, you would see that light travel time change, and we could record that at the output of the device. So that was Weiss's first idea. he also was the one who recognized, because of Thorne's number, that 10 to the minus 21 number, the wave is so small, he was the first to recognize you could not do this in a lab with a small interferometer. You had to make it very, very long, because the amount by which the mirrors move is proportional to the distance between them. So he came up with this important thing, which was delta L is how much does the mirror move. It's proportional to the amplitude of the gravitational wave h, and it's proportional to the distance between the mirrors. So he said, well, you can't do this with just a small distance. You have to make these detectors kilometers long. And he came up with the number 4,000 meters, or 4 kilometers. And once you do that and you put the numbers in, you have to measure motion of the mirrors at the level of 10 to the minus 18 meters. So let me put that in perspective. It's not a smaller number as 10 to the minus 21, but it's still damn small. Now, what is it? It is a proton. The nucleus of a single atom has a diameter of 10 to the minus 15 meters. This is 1,000 times smaller than the nucleus of a single atom. So it's a horribly small number, but Weiss kind of looked at it and said, okay, this looks like it's doable, and teamed up with Thorne, and together they went about getting an experiment funded and built. And a very bold experiment was born from their collaboration, which is the LIGO experiment. It's the Laser Interferometer Gravitational-Wave Observatory, but we will just call it LIGO. LIGO eventually became 2 long detectors, one in Washington State in the northwestern United States, and one in Louisiana in the southeastern United States. They are indeed 4 kilometers long each. And they have all of the technologies that you would need to make a measurement at the level of motion of mirrors of 10 to the minus 18 meters. So to do that, you have to have a lot of vibration isolation to sort of protect the mirrors from other terrestrial forces. You have to make the smoothest mirrors in the world to catch all the laser light that travels down those 4 kilometers. You have to have a very well-behaved and powerful laser, and many, many other things that I won't tell you about. And this was all put together in the US, at least, by decades of support from the National Science Foundation, which we'll hear more about also later in the session. So on September 14, 2015, the detectors of LIGO were on the air, and they saw an incredible journey of a gravitational wave. So here are 2 black holes that do what Einstein instructed them to. They collided. The gravitational waves from the black holes spread out into the universe. And then, 1 billion years later, they arrive here at our pretty little Earth. And who should be around to detect them but the detectors of LIGO? So here they are. They come through the Earth. They cause tiny distortions of the Earth. This effect is really, really, really exaggerated. They arrive. They arrive at the Louisiana Observatory first, and then 7 milliseconds later they arrive at the Washington Observatory, and we can record that as a signal. And that's the 2 data. They have been shifted to put them on top of each other, and that was the signal that we recorded. There are some important things to notice about it. The first thing to notice is that the vertical scale sets the size of the wave, and that strain, the amplitude of the gravitational wave, indeed was 10 to the minus 21 at its maximum, just where the 2 black holes collide. This corresponds to a motion of the mirrors of about 4 times 10 to the minus 18 meters. So it's a triumph both of those original predictions of gravitational waves and also of the power of the instrument. What we could learn from this data, and the time scale here is a fraction of a second. So this is amazing. These black holes live for about, for 1 billion years, and we have captured their death in the last few seconds before they die. Okay, what do we learn? We learned that these black holes were pretty heavy. They were 30 times the mass of our sun. They went at the time that they collide, and now here is this concept which resonates with the theme of the festival. At the time that they collided, these black holes that are 30 times more massive than our sun were whipping around each other at half the speed of light. Okay, this can blow minds. And so they were 1.3 billion light years away. And the other remarkable thing was that the new black hole that formed was actually lighter than the two original ones by about 3 solar masses, and that was the energy that was radiated away into gravitational waves. So it was a spectacularly violent and powerful collision. Now, I just want to put this in perspective. So it was the first time we had directly observed the ripples of space-time. It was the first time we had directly seen two black holes collide like that, and that was the first time we had been able to test Einstein's theory in this regime of black holes. But the real excitement is that this is the first time we've been able to look at an object in the sky that gives off no light. If we had pointed our most powerful telescopes at these black holes, we would have likely seen nothing. We are, for the first time, using gravity instead of light to observe the universe. Now, Galileo did something similar 400 years ago. In 1609, he pointed the first telescope at the sky, and his findings were pretty modest. He saw craters on the moon. He saw that Venus had phases. And so by our standards, today we can do that with binoculars. But the paradigm shift was that we no longer used our naked eye, that we were able to use instruments to look at the universe and at the sky. And since then, we got better and better at making amazing instruments in adding all kinds of different colors and precision to these measurements. And I think that's where the observation of gravitational waves is. We have this global network of detectors that are coming up all over the world, the two of LIGO in the US, but also in Europe, Japan, India, and indeed even a space detector. And so I want to finish just by saying in the last year, LIGO detected 3 black hole collisions. The first one is shown in green, was the one whose data I showed you, and since then it detected 2 more in October and December of 2015. And I just want to emphasize this is just the beginning. As these detectors get more and more powerful and as more and more detectors come up, we should be able to map out the entire sky in gravitational waves. No longer do we use just light, we use the gravity of the universe to tell us what it's made of. So thank you.
Thank you. That's wonderful. Thank you very much. I think you've done a great job of giving us a sense of the tiny, tiny scale and also the massive scale. And the two are intimately, they're the same thing. The visual event was enormous, but the ability to detect it required something very, very small. In reading a little bit about the researchers, I ran across one quote which I thought was wonderful. The researcher says, the effect we're measuring on Earth is equivalent to measuring the distance to the closest star, other than the sun, the closest star, Alpha Centauri, to within a few microns. Or as Nergis told me, the width of a human hair. And then he says, with admirable understatement, it's a very tough measurement to make. But you also heard from Nergis that Ray Weiss did all the calculations and said, yeah, I think we can do this. So these people come to you when you're at the NSF, and they say, we think we can do this. And what do you say to them? I mean, how do you take these kinds of requests?
Well, it didn't come to me.
Right. Okay.
I liked what Nergis said, and then they had the idea, and they built it. That the time between that idea and getting these things constructed is something I'd like to say a little about. And that is the sort of political and science policy issues that go into funding and constructing major research projects. Let me say a bit about the National Science Foundation. You'll need to know that to appreciate how this comes about. The National Science Foundation was founded just after World War II to fund basic research. Anyone connected with a university or scientist probably gets funding from the National Science Foundation. And it was founded and continued on the premise for years of responding to requests from scientists. So the foundation is not a mission agency like the Department of Energy, which has a certain mission and it puts together funding and it will request scientists to do the research on their behalf. The foundation's way of operating is that scientists send in proposals. They send in ideas, and we have various panels, peer-reviewed it's called, that review these ideas, and the best one bubble up and get funded. And it was called looking at individual investigators, rather small grants, A large grant could be a few $1 million over the, say, 20 years ago. It can be 10, 20 now. That's still rare for an individual investigator. So the idea of a big project, as LIGO turned out to be, $200 million project, was not something that the foundation had been doing as part of its mission and its history. Also, another issue surrounding LIGO, I'll show you a graph to walk you through that if I might, around LIGO, is that you notice it's called an observatory. This is a very controversial notion within the scientific community, especially the astronomy community, because it implied that this would be a device that would be a continuing instrument to observe space rather than an experiment. There was a lot of push from the astronomers that it should be just an experiment, because you do the experiment, you detect gravitational waves, you proved it, move on. And also, within the federal funding community, there's always competition for the available amount of funds. So this was going to eat up quite a bit of funds out of the NSF's fixed budget. So maybe if I could just show,
Sure.
how do I
show
do
us a
that?
little bit? Yeah.
Walk you through, what do I do? Push this? Nope. This. Well, I'll turn it off. Push this. Oh, there we go. What do I do now?
You got to point. You got to point it out.
Oh, this way.
Okay.
All right.
He's
I'm a theoretical physicist. I am. So I never went into the experiment. So the first ideas of Kip Thorne and Ray Weiss came to the NSF in the early 70s. Actually, before that, they had some of the ideas. But you see, this is a graph that shows the funding over the years. And you see it was a relatively small amount of funding, less than $1 million. And there were a number of reviews, and I'll show you a slide to walk you through all the reviews so you get a sense of how complicated it was. But they kept passing through these certain filters of reviews, and finally it reached the point here in 1990, you see the slide, the big bump in construction, where the National Science Board, which is the governing board of the foundation, finally approved the project. So that's from the time they first started to the time of the detection of the waves. What's that, 40 years?
40 years, yeah.
40 years. So indeed, we're measuring speeds and short distances, but the time scale can be very long, not 1 billion years, but in the life, it's almost a third of the life of the scientist, given their age.
Right.
It's close to half of the life of a scientist can be spent on a project like this. And I'll just show you the next one. So I don't want you to read all this, but it just gives you an idea of the process. So in 1983, this was reviewed by an advisory committee. This is a committee of scientists. It's not the federal government officials or not Science Foundation employees. It was reviewed by a committee of scientists, an advisory committee. 84, it went to the Science Board, got an initial approval. Then it had to go to OMB, the Office of Management and Budget, to be put in the federal budget just as a part of a feasibility study. In 1985, we had another review. Caltech and MIT were jointly overseeing the project. Ray Weiss is at MIT, Kip Thorne is at Caltech. Then it had another peer review from this International Society of General Relativity and Gravitational. They endorsed LIGO, but they said it was an endorsement. They endorsed another way of detecting waves using Weber bars, which was much less expensive and were easier to build, and in fact, they had been tried before. So they still weren't totally on board with LIGO. And then another outside review committee endorsed it. The NSF, we had site visits, construction proposal in 89, the board approved it again in 90. Then we had to do a risk analysis, and finally, we got down to the approval in 91, and the site choices were announced in 92, which really sealed the deal, because anytime you get into funding projects which are going to be placed in anybody's congressional district, that has to be taken into account. Right. And so I can stop, then we'll come back to that a little later. But actually what What got us the funding, I'll say it now, is that we had a review of all possible sites that would fit. They had to be a certain distance apart. And they brought to me finally 17 different sites, and you could do about, maybe over 100 different combinations of those different sites. We had them all reviewed for their suitability, the environmental issues, the vibration issues, and all of that. And then we had to choose the final 2 sites. And Senator Bennett Johnston was then the senator from Louisiana, ring the bell, Louisiana. And Senator Johnston also chaired the Senate Appropriations Committee that oversees NSF funding. Congressman Bob Michelson chaired the House Committee on Appropriations Subcommittee, and his district is Livingston, where LIGO has one leg. The Speaker of the House, Tim Foley, his district is Hanford, Washington. So it just turned out that those 2 sites happen to be the best sites we could choose. What a coincidence. But actually, we were very transparent about it, and they all had to fit, and so it was just a fact of life, a fact of political reality. If you wanted to get this built, you had to get it through Congress. You had to get the funding, and they helped us get the funding. Right. So I'll stop there.
That's great. Yeah. I mean, as both of you have described already, we have multiple people thinking through the numbers. We have huge numbers of people thinking through the technological requirements, the technical requirements for what these mirrors are going to be like, how big the things have to be. And we have dozens and dozens of people at NSF working. I think there's over 900 scientists.
Over 1,000.
Over 1,000 scientists working worldwide on this. We see now there are more sites for detection. You know, when NASA does something, you see them all like, high-fiving. It landed or it met, and they all like, yay! They go. Did you guys do that? Did that happen for when the gravitational waves? I mean, what is the kind of collective feeling, or is it a personal feeling of pleasure and joy and satisfaction when you both heard about the gravitational waves?
Sure, I'll start. So, in a field that has been so signal-starved, we were very cautious. And so when we first saw the signal, we were actually completely skeptical. We thought, oh, this can't be a signal from nature. This is something we've inflicted on our own instrument. And so it took actually a couple of weeks of really careful checking and double checking to make sure that it wasn't something like that. And so there was this moment of goosebumps when you first saw it. Then you're like, oh, no, this can't be. And then there was a period of sort of slowly growing excitement, certainly for me, and many of my colleagues will say the same thing. But there was a moment right around the early October when we had completed all the checks and when another analysis of the data revealed its results, when we kind of knew, okay, this is really it.
Yeah,
and then
the detection was in September, but you didn't. I don't think the public announcement was till the winter of 2016, right?
February 11th, 2016.
And that was because of you wanting to make sure you had it right.
Exactly.
Yeah.
And so, but by October, we kind of knew that it was real. And then we had a whole bunch of other things to do to get the parameters right. Were there 30 solar masses? Were there 20? Were they, 1.3 billion light years away? Were they, in our backyard? Those kinds of things. So.
Did you feel vindicated?
Well, not just me, quite a few people.
Yeah.
It's quite a long time, right? 92, 2016. And over the years, Nergis didn't mention it, but the original LIGO had been upgraded several times to make it more sensitive. And those of us who were involved earlier, if you would hear a rumor, I heard there's a signal, and it was sort of spread around the internet. No, that's nothing. I heard first, I received an email from a colleague named Bill Harris, Dr. William Harris. He was head of the Mathematical and Physical Sciences Division, and that's the division of the NSF which actually oversaw the funding for LIGO, and he had been one of the people most involved. He's now out in Arizona. He sent an email and said, I think it's real this time.
Wow.
I've heard from Kip, that he'd heard from Kip Thorne. And then I got an email from Kip, and I said, maybe there's going to be an announcement tomorrow morning. The current director of the National Science Foundation, France Cordova, is going to make an announcement about the wave. So yeah, that was excitement.
Oh, yeah.
And I think what made it really fulfilling is that the scientists had stuck with this for so long, and also the foundation and Congress had continued to fund it. And I think there's another lesson here about these major discoveries. It really takes a long time commitment, and we're fortunate, I think, in the United States that in spite of what you read in the papers about and what's true about maybe less than a functional, ideally functional Congress, they have, the Congress in the United States under each party, I found over my career, have supported science. I mean, up and down, but they have supported it. And I think we've been very fortunate.
Yeah, I mean, I believe the LIGO was about the most expensive project NSF has funded over the years. Is that about right? Is that?
Yeah, that's right.
Yeah.
Yes.
And I was very struck by your comment, I hadn't realized this, that there was some dispute about whether this was an experiment or an observatory. And it sounds to me from the way you were describing it, Nergis, that there, and the things that have been detected since, that the observatory idea really is the case. I mean, we have now the ability to regularly observe some kind of signals that are not light. And this is a game changer, it sounds like. So the observatory people seem vindicated too.
The astronomers have come around.
Okay,
oh,
good.
Yeah, she's an astronomer.
Okay.
Astrophysicist, really.
Yeah.
But,
yeah. I think the sentiment in the scientific community has also changed. People now widely embrace it as an observatory that's going to partner actually with telescopes that look at light to start doing combined observations. So
Let's talk about, to go back to the funding right now, there's a movement to have more private funding, more private philanthropy. You're involved in a project right now that's privately funded, is that right?
I am.
Can you tell us a little bit about that, and we can come back to the funding patterns, where we are?
I can, and actually, Nergis showed a slide. It's called the Giant Magellan Telescope. It's under construction now. We're beginning in Chile. It's being built by a consortium of 6 U.S. universities and 3 institutions from other countries, Korea, Australia, and Brazil. And it will be the world's largest telescope when completed around 2021, 22 as of now. And it's a beautiful, fantastic engineering feat. It consists of 7 mirrors. Each mirror is about 8 meters in diameter, so the effective diameter of the telescope will be about 25 meters. It will be the nearest to that now are 10-meter telescopes. So this would be almost 2.5 times as large as the largest telescope. And the more light, you're an expert on this, the more light you collect, the more information you collect, basically. It's interesting, two aspects of this I'll come in. One is science, and I'll ask her to verify this, but I know about it. But the funding. Telescopes traditionally are not funded by the federal government, ground-based telescopes. People are not usually aware of that. The Hubble telescopes, space-based telescopes, NASA telescopes are funded. But Nergis also showed a slide that showed the history of telescopes up there with the Palomar, one on Mount Wilson, and all of those are privately funded. Andrew Carnegie funded those first 2 smaller telescopes in California. So this will be about a $1.2 billion project, and it's all, NSF may fund some instruments that go on it, but all of the construction was money that has to be raised. So we've raised about half of that. So does anyone want to contribute to a telescope? Meet me at the door. Right. The other thing I told you, well, what is it, how does this intersect with LIGO? Once you have another detector that you can triangulate on the source of the gravitational waves, you can provide an opportunity for this telescope, maybe GMT, to look at that area of the sky where that collision took place. And I gather, Nergis, from what I'm told by my astrophysics friends, is there's uncertainty as to what you're going to see, but there's so much energy that people think you're bound to see something. Maybe you say
Yeah,
more.
no, I think that's completely right. And that's actually something that people call multi-messenger astronomy, which is your messenger is light and your messenger is gravity. And the idea there is that in particular for objects like neutron stars, we believe that when neutron stars do this dance around each other and collide, they actually give off a burst of gamma radiation, for example. And that should have some other wavelengths of light in it as well. And so the way that you can fully construct what an object in the sky looks like is to use all your senses. Like the analogy I like to use sometimes for this is, it's like going to a silent movie and then suddenly someone turns the sound on for you. And that's how you reconstruct so much more information. That's what we're trying to do here with telescopes like Giant Magellan Telescope and gravitational-wave observatories.
I wanted to bring us back to the Humanities Festival and science. And I have a quote for you from Edward Wilson, the entomologist. He says, "The ideal scientist thinks like a poet, works like a bookkeeper, and all too rarely writes like a journalist." I want to thank you both, first of all, for being so open and clear about these very difficult matters. And you've been kind enough to agree to appear here at the Humanities Festival. The question is, what do you think, how do you think the scientists and humanists intersect? What do we share in our work?
I can answer that in one word, and it's creativity.
Okay.
I think it's just, I think wonder and creativity. You think about how the world works, or you think about how the mind works. You think, whatever you think about, as long as you're curious and creative, you will discover new things.
Okay.
I completely agree with that. Some of you heard that towards the end of my career, I've now become immersed in the world of arts and design.
Right.
And when I was first asked to become president of SAIC, the School of Art, the Art Institute of Chicago, I wasn't sure what I could bring to that or how interesting it would be to me given my scientific background. But you find what underpins all these fields in which people have to be creative, who think beyond the ordinary, is this sense of curiosity. And a determination and almost an obsession with pursuing their curiosity. And I have a couple of slides that I'll show, the quotes that I like, which I think says something about the human side of science. By the way, this is a very readable book. You don't have to be a scientist. I really recommend it. It's by Carlo Rovelli, who's an Italian scientist, and it's called 7 Brief Lessons in Physics. And I'm going to read it. It said, "Before experiments, measurements, mathematics, and rigorous deductions, science is above all about visions. Science begins with a vision. Science thought is fed by the capacity to see things differently from how they've previously been seen." And that's true for humanists, true for artists. And for LIGO, there's a book called Gravity's Shadow, which really is a detailed history of gravitational waves and LIGO, by Harry Collins. It's a rather thick book, but this is a quote I like. "The search for gravitational waves is a heroic and exemplary passage of human activity. It counts among the things that make it worthwhile to be human." And I think that connects with being the humanities.
Yeah, yeah. A couple of weeks ago, we had Lin-Manuel Miranda, and he used a phrase. He thinks of his work, his artistic work, as a matter of meeting the moment. That he has to prepare rigorously over a long period of time in order to meet the moment when it arrives. And this certainly sounds like the LIGO thing was very much that. Just get ready, 100 years, since Einstein's first prediction, build the things and just wait. And then, bloop, what does it sound like? That sounds like that, right?
It kind of actually, yeah, it sounds a little bit like that. If you could track it, for a little bit longer, it sounds like a chirp, it goes, whoop. But you're extending it there, right? You're making it a little bit more audible for us. In some cases, in the case of the signals that I showed, those are kind of more like a thump, because that's they're at lower frequencies. If you could track them to higher frequencies, you would hear a little bit more of a. Yeah. But yeah, it's roughly that.
So creativity, being able to be curious and to stick-to-itiveness. Almost is a basic, and I think that's shared also by artists, and I think that's absolutely correct. Thank you both so much. We're going to give the audience a chance to ask some questions, so I guess you could bring the lights up, Dana?
We have a question over here.
Please speak into the mic. Thank you.
As scientists, do you have a specific measure of how you measure objects affected by another object's gravitational waves? For example, the Earth affected by the sun's gravitational waves?
Good, so I'll take a shot at that. So it turns out that the Earth-Sun system could generate gravitational waves under certain circumstances, but it turns out the gravity around our sun is kind of pretty weak. It's not a very massive and compact object. If the Earth were to shrink down to a few kilometer radius, then it would start to have some appreciable space-time curvature. And then if it also performed accelerating motions, then we would get some waves. But it's pretty negligible for this system, for the entire solar system.
Actually, two questions, one on attenuation and then duration. In a three-dimensional universe, we know that waves, the intensity of a wave happens to decrease as the inverse of the square of from the source. So the first question is, do these gravitational waves attenuate according to that formula? And the second, duration. When the event happens that the two black holes come together, boom, and do the waves go out and that's it, or do they continue to go out after the implosion, if you will?
Yeah. So the answer to the first question is the attenuation, yes. So the thing that we measure is actually not the power in the wave, but the amplitude of the wave, just the size of the wave. So it actually falls off as 1 over the distance, not 1 over the distance squared. So that's the attenuation rate. And then the question about what happens, is the wave continuously being generated, or is it you can think of this particular event where where the bulk of our signal comes from the moment when the black holes collide. So as they're orbiting each other, we're getting the signal and it's coming continuously. But after they collide, the new black hole that forms is no longer accelerating. It's just kind of wobbles and then sits quietly in darkness, and so the signal shuts off, actually. It's a little bit like dropping the rock in the pond. The ripple spreads out, but after a while the ripple is attenuates, but there's no continuous ripple. Just one ripple went out and that's it.
You mentioned that these two quasars were circling each other at about half of the speed of light.
Yes.
Do things actually, I guess I'd never thought about it, do things actually go half or 3/4 of the speed of light? These are at unimaginable speeds. They're almost to the speed of light, but they're not quite. And these are physical objects.
Absolutely. You are completely right to be puzzled and perplexed and even frightened by it. So normally when you think of things that are traveling close to the speed of light, they're microscopic particles like electrons and so on. When you think of objects that have 30 times the mass of our sun and are kilometers big, whipping around at the speed of light, that really only happens in these very extreme events in the universe.
How often do you expect to get a detectable event?
So that's a very fine question. We, in this first observing run of this, improved phase of LIGO, we call advanced LIGO, we measured for 3 months and we saw 3 events roughly. And so if we make no improvement in sensitivity, you would say that that's about the rate, 1 per month. But actually, for the past year, the detectors have not been in observation mode because we're actually putting in new subsystems and making improvements. So once they improve, that rate should go up even more for black holes. But there are also other kinds of sources that we hope to be able to see, like the collisions of neutron stars, for example, and those have slightly different rates.
In pure research, we've seen things come to actuality in many cases, and I'm just wondering, in your opinion, is there any, we've verified a theory, so is there any application to this in the real world?
Mm-hmm. Yeah, so it depends on how real a world you live in. So the applications, yeah, so I think we have verified a theory, but we've done something a little bit beyond that, which is the paradigm shift that I talked about. We have, for the first time, now said we have a tool here, these gravitational wave telescopes, or detectors, if you will, that can actually observe those parts of the universe that are actually completely dark, but have these extremely violent events occurring that we can only see by using gravity. So I think there is actually, so that's an application. Now that may not sound so real world to you because thankfully these systems are very far away from us. But really what's behind it is black holes, for example, or neutrons, as many of these things, these are the building blocks of our universe. These are the ingredients you have to pour in to make the universe look the way it does. These are the same things you need to understand. Where did all the chemical elements come from? And ultimately, where did we come from? So I actually think that these are, even if you don't care about just the pure distance and discovery of it, these answer more fundamental questions about our own origins as well. And that, to me at least, feels pretty real.
But there's also other things that come out of these big projects. In fact, LIGO has, you go on their website, and they have a technology transfer website that shows the kinds of things that have come out of the instrumentation and the detectors. That, the sophistication of these detectors, right, to measure these brief distances and amplitudes of the waves is something that didn't exist. These had to be developed, invented for this project. And they will have applications in other areas where you might need to measure, micro vibrations or detect small signals coming from small objects. Could be of various kinds. So that Nergis answered on the science part of it, but these kinds of projects usually do have technology applications that come out of the projects themselves.
What's the next moonshot of fundamental science? If I was going to give you $1 billion tomorrow, what would you be excited to discover next?
$1 billion wouldn't buy you that very much for a moonshot. That's first of all. Sorry.
Yeah.
Go ahead.
I think almost any scientist you ask will give you a slightly different answer. And I think if, looking out into the universe, my answer would be we have this enormous mystery at the moment of what dark matter and dark energy are. And we know that without those two things, our universe would fall apart. So they're important, they're there, but we don't know what they are. So that would be one example. But that's, if you wanted to look at the universe. I mean, I think if you wanted to look closer to us right here, I think understanding the brain. And I imagine, Walter, you have a completely different set of things you would love to have a moonshot at.
Well, the Giant Magellan Telescope, one of the things they are going to be able to give us a lot more information about is whether they are habitable planets that we can see. You've heard about exoplanets, planets outside of our own solar system, which seem to be, in some cases, in what they call a sweet spot, that perhaps you might find the conditions for life as we know it. But we can't really detect can't see enough yet to detect that. And the Giant Magellan will be able to see spectra coming from, if there are chemicals on there that fit within the range of chemicals that support life, the Giant Magellan Telescope will be able to see those. So whether there's life on other planets is, I think, another thing that we, as a species, we are certainly continually curious about, sometimes frightened about. So that's not quite a moonshot, but that's, I think, one of the things that we're looking for on the horizon.
Dark matter, life on other planets, the workings of the brain. Is that good enough for you, Nick?
I'm right there with you.
Thanks.
Hi there. I understand that space can be changed dramatically by these violent effects, neutrons colliding or black holes colliding. But when I think about the gravitational waves, I'm very excited about this idea of the crest of the wave and the well of the waves. And if those areas of space have changed at a subatomic level, once space has been affected by these waves, what happens to that area of space itself?
Yeah. So that's a very elegant question. There are some very special places in space where the space itself would have memory, like a memory foam, where some, the peaks and troughs went through and then it somehow remembers. But those are in very extreme places like near black holes, and we're not even sure. These are completely unmeasured. These are speculative ideas. On average, when you look out at space and a gravitational wave goes through, it leaves no imprint of having passed through. It's very much like as a ripple on the pond goes by, once the ripple's gone by, pond's nice and quiet again. So,
I read a couple of years that scientists have postulated that there are other universes, that we're not alone, that they're just, who knows? Does this kind of observation give any evidence of something like that?
Yeah, well, would you like to, or should I?
No.
Great. So you're absolutely right. There has been a lot of thinking behind the question of what we call the multiverse, which is not that we're in a single unique universe, but that there's other universes that are actually inaccessible to us. And so does this discovery help that question? It's almost certainly no. Now, where could you go with imagination on it? That's actually a little bit of fun. One of the ways in which people think about how one might access a parallel or alternative universe is to dive into a black hole. And who knows where you'll come out on the other side. You will never be able to come back out into this universe. So it has some poetic connection to it, but I think in terms of what we know, the answer is we don't know.
Let's thank Walter Massey, Nergis Mavalvala.